Welcome everyone to Unit 5, Section 3. Here we're going to be talking about power and how it relates to forces and work. All right. So when we think about power, most of the time we think about really strong people or really strong things, but that's not necessarily synonymous with each other. It means they're not necessarily the same thing. And we're going to see that here in just a moment. So when we define power, we're going to define power as the amount of work a force, something can do, some kind of force can do in a given amount of time. So it's not just about what the force can do, like how strong it is and how far it can move something. That would be work, right? Remember, work is equal to the force times the distance times the cosine of the angle. We can also say that sometimes the work is equal to the change in kinetic energy, or maybe the work is even equal to the change in gravitational potential energy. It really depends on what our force is doing. So when we take our force times our distance times our cosine of our angle, we're going to get how much energy we are going to transfer or change while that force is doing its work. But it's not just about that when it comes to power. Power is also about how quickly you can do that, and that's the time part of it. So two forces might be able to do the same amount of work, but in the end, if one can do it faster, then that makes it more powerful. You know, I think a great example of something like this would be a really big linebacker in football. They might be able to lift a lot of weight, and maybe they are very, very strong because they have to push very large people in front of them. But then maybe somebody else who is much, much smaller is much, much faster. So maybe they can get themselves moving much more quickly. So they do less work, but they do it so fast that they could actually be more powerful, right? So as we look at power and power ratings for things like engines or people or any kind of force, then we're considering those two parts, the work that they're doing and the time that it takes to do it. So when we talk about work, we're talking about joules, right? We're talking about joules of work. And when we're talking about time, we're talking about seconds. So when we're looking at the units for power, we're talking about joules per second. All right, so how many joules of energy can be changed or transferred by a force in a given amount of time, each second, to be specific here. Now, a joule per second is a kind of a messy unit here. So we actually usually call these watts, and we use a W to help us out with that. That's our abbreviation for watts. Now, I'm going to point this out because look how this can get a little bit confusing when you're solving problems, right? If power is in watts and work is also a W, you got to be careful. This one's a unit. This one here, this is a variable. And the variable with the units per work being joules. All right, so be really careful there. As long as you're paying attention, I don't think you'll make too many mistakes with that. So maybe we're familiar with watts being on things like light bulbs, right? Or maybe even electric motors. And generally here in the US, we think about watts as being something related to electricity. But it's really any power rating is considered to be in watts. In the US here, when we talk about engine stuff, we generally talk about horsepower, all right? And, you know, that's a funny old thing that kind of came from a guy that was selling motors back in the day and trying to convince farmers to purchase his motors, but he had to tell them how much work one of these things could get done in a day. So he came up with the horsepower to help him sell his motors. And we still kind of use that today because I guess that sounds cool, right? So what makes a force more powerful or less powerful? Let's start with an example, all right? So we already know it's about work and it's about time, all right? So let's look at an example of, say, a power lifter. All right, so a power lifter is some, you know, big burly dude here, okay? And that big burly dude is going to be, you know, picking up some kind of weights. All right, make a barbell here. All right, big burly dude, shorts. So this big burly dude is going to lift these weights up. Let's say we have a mass of, oh, let's call it 100 kilograms, right? And so maybe some power lifter out there is out there laughing at me. But so this guy's going to lift these weights up. They have a mass of 100 kilograms, and we're going to lift them from one height. We'll call our initial height 0 meters. And you're going to lift it up in this direction until he reaches his final height. All right, let's call it 1.65 meters. You're going to lift it up above his head. All right, so he goes from the floor up above his head, lifts it that distance. Well, how much work is he doing? Well, his force is resisting that force of gravity, picking up those weights, and changing the gravitational potential energy. So the work done in this case is the change in gravitational potential energy, which we know from this equation we can calculate with our initial and final heights, our mass, and the acceleration due to gravity. So if we quickly do that, we can find out how much work this guy's force can do to lift this 100 kilogram mass. I'll give you just a moment to do that calculation yourself. So here we have our mass of 100 kilograms, our acceleration of 9.8 meters per second squared, and we have our final height of 1.65 minus our initial height of 0 meters, just like so. So the work that this man does as he lifts this thing up is going to be it's going to be 1,617 joules worth of work. All right. Now let's consider for a minute like what it would mean to be more powerful. So regardless, if somebody is going to pick this thing up by 1.65 meters, they're going to do the same amount of work every time. So what makes one person's force more powerful than another? What makes it more powerful is how much time they do it in. So if one person lifts this up and does that work of 1,617 joules, and let's say the first person does it in 2 seconds, all right? So delta T is 2 seconds. Then how powerful is this? So power is equal to the work done, which in this case is our change in gravitational potential energy, divided by the time that it takes to actually do it. So we have 1,617 joules divided by our 2 seconds, all right? And we get 808.5, and this is joules per second, so that is watts, all right? So that's the rating for the power if they can actually do this work in 2 seconds. How does that change if somebody does it more quickly? What happens if, say, our time is now half of a second, which is crazy fast, right? So in this case, we have our power, again, is our work divided by our time. The work doesn't change because we're still lifting this 100 kilogram mass by the same 1.65 meters. And so we have 1,617 joules. But this force does it in 0.5 seconds. This one's really different, isn't it? Look at the difference here. So because this force can do it in that much less time, right, about 4 times less time, it actually makes it 4 times more powerful, right? 4 times more powerful. And that's because we're doing the same amount of work, we're just doing it in less amount of time, all right? So that's really what this is all about. And we can have different changes in different types of energy. If you had a car, the work that was being done on your car is likely going to be the amount of work that it takes to change your velocity, right? So we might have an initial velocity maybe of 0 meters per second, right? And maybe a final velocity of 20 meters per second. And so this car maybe it has a mass of 600 kilograms, is going to be changing its kinetic energy. So the work that's being done is equal to the change in kinetic energy in this case. All right. So some cars do this quickly and some cars don't. All right, your really awesome cars might do this in like 2.1 seconds. All right, whereas maybe we'll call that awesome. All right, and then not so awesome, which is my car, is probably going to do this more of a time in like 12 to like some mornings it seems like it's 25 seconds to get up to maybe a speed of 20 meters per second. I'm going to need a new car. All right. So this awesome car is going to have more power than this not so awesome car because it's doing the same amount of work to change that kinetic energy in a shorter period of time. All right. So essentially that's what power is. And in the next video, you're going to see some calculations and some examples. So good luck.